Hello everyone, my name is Guillaume Fieni. I'm a PhD student at the University of Lille, and today we present you SMARTWATTS, a self-calibrating software-defined power meter for containers. Data centers try to maximize their power usage effectiveness in order to reduce their operating cost and their carbon footprint, and to improve the management of their resources. This requires the ability to highlight energy hotspot for distributed infrastructure, especially heterogeneous environment like HPC, cloud computing, edge, at a fine granularity, so hardware for CPU, memory, GPU, and software, virtual machine and containers, and taking into account various kinds of workloads. In the literature, there are a lot of work about hardware parameters and software parameters, and for hardware parameters, there is a multiple levels of granularity, from the power supply to the specific electronic components, but they require specific hardware to measure the power consumption, so they are difficult to deploy because you need to modify the hardware of the machine. They are difficult to scale because you need to deploy the parameter to every node, which can be very costly. So the community have developed the software parameters, which are mainly model based, so they need to be calibrated. So this calibration can take a very long time, sometimes it's just minutes, sometimes it's days, and it will be mostly resource intensive because I will run some benchmark over a very long period of time, and the workload used need to target the monitoring system. So this is that the software parameter highly dependent of the input workload, and they will be tailored for specific hardware. So we propose the SMARTWATTS, which is a self-adaptive power meter, which provides a per container CPU and memory power estimation. It is lightweight, there is no external hardware required, and it's based on the Power API framework, and is freely available on GitHub. Power API is a middleware toolkit for building software-defined parameters. It is written in Python. It's maintained by the Spiral team. It's open source, and it's also available on GitHub. There is a lot of example and an extensive documentation, so it's very easy to use. In order to evaluate the accuracy of the software power models, we require a reference power measurement. So in this case, we will use running average power limit, RPL, which is a feature that provides a power capping capability for package and the memory. It also reports the accumulated energy consumption for multiple domains, so the package, the core, the integrated graphics, the memory. It is available on Intel Sandy Bridge and AMD Zen CPUs. It's known to be accurate. There is a lot of work that use RPL for its power estimation, and some work evaluated the accuracy and conclude that it's indeed accurate. So we choose to use RPL to provide the reference power measurement in order to know when to trigger the learning of a new power model. For accounting the resource usage of the application, we are using hardware performance counters, which are known to be low overhead. There is a very high amount of available events to monitor the various aspects of the CPU, but there is a limited amount of slots to monitor the events simultaneously. So you need to select the most relevant events for your usage. In our case, we are using the correlation coefficient with the reference power measurement provided by RPL. So our contribution is based on the monitoring of the software containers. and this is, in our case, is based on the Linux control groups, which are used by Docker, Podman, Leavitt, and systemd, and a lot of other tools. And it allows to monitor the performance counter per container by using the perf event interface. So the power models are used to distribute the reference power measurement of RPL to the running targets of the machine, also the containers. In our case, they are learned at runtime, so there is no offline calibration phase required. We use the machine activity and inactivity as samples for the learning, and the goal is to build the robust power model over the time. So the power model are frequency specific, and each frequency have a sample history and a power model. And this allows us to take into account the power consumption optimization of the CPU, like the C states, which are the idle power saving states, which are active when there is no execution on the core, and there is the P states, which are a voltage and or frequency tuning that are active when there is an execution on the core. So the per frequency sample history is a moving window for n samples, which is configurable, and it allows us to keep the current content of execution, which will be used when we learn a new power model in case we exceed the error threshold. The power models are based on the multivariate linear regression. So this is used a lot in the literature because they are very efficient, they use very low resources, and you can have a very good precision depending on the samples. In our case, we are using the elastic net regression, which is robust to outliers and can perform feature selection, which are necessary because the hardware performance counter can have a collinearity, and this allows us to remove some of them when they are unneeded. Our contribution is use mainly 3 software components. So there is a sensor which will be used to monitor the hardware performance counter on every node. There is a power meter, which will use the sample of the sensor to compute the power estimation for every running containers. And the database, which will store the samples of the sensor and the power meter. To evaluate our contribution, we choose to focus on 3 main attributes, like the quality of the power estimation, the accuracy and stability of the power models, and the overhead of SMARTWATTS on the monitor host. To do so, we use 2 environments, one HPC, so it is a single node, and the second a cluster of 5 nodes. For the workload with benchmarks, so the NAS parallel benchmark, which is a collection of HPC benchmarks, and StressNG, which is a collection of a lot of small benchmark. And for the cluster, we use a producer-consumer data processing pipeline. For the power model accuracy, especially for the package, we choose to use a 5 watts error threshold and 1 watt for the memory. We can see on the table that for the machine which have 2 sockets, the mean of the error of the models for the package is less than 5 watts, 2 watts for the socket 0 and 3 watts for the socket 1. And for the memory, you can see that we don't exceed the 1 watt threshold too, and we have 0.5 0.3 watt overall on average. For SmartWatts power model stability, in our experiment we show that SmartWatts succeed to reuse a given power model up to 594 estimations, but the stability strongly depends on 3 points. First, the sampling frequency. When you have an higher frequency, it allows to converge to a stable and accurate power model more quickly. The error threshold. When you increase the error threshold, it leads to more stable power model because you tolerate more fluctuations in the estimation without changing the power model. And the input workload. When you are running a stable workload, like benchmarks or the inactivity of the machine, you will have a more stable power model. But in the case of unstable workloads, you will have obviously more power models because you need to try more before having a stable one. However, we show that learning a new power model is very fast. It takes less than a millisecond and it uses very few resources, so the overhead is very low. To evaluate the overhead of SmartWatts, we choose to implement its component as a container, so SmartWatts can monitor itself. And this shows that the sensor has a very low impact on the monitored system. This is mainly due to the usage of the hardware performance counter that don't induce runtime performance penalties, and reading the performance counter use very little resources. So this leads to a low power consumption of the sensor, as we can see in the table, that the consumption for the package and for the DRAM is very low. This is important because the sensor will be deployed on every node of the cluster, so its cost in resources and energy should be low, and impacting the execution of other software is unacceptable for a production environment. SmartWatts is able to provide a per container per estimation overview. So on this example, we can see there is a kernel, system, and different benchmarks running on the system. For the benchmark, they are using a different amount of cores, so 8 or 16. The benchmark start at the same time, and we can see that they stop at a different time. This shows that SmartWatts allow to highlight energy hotspot for containers running on a machine. SmartWatts can also provide a distributed service overview. So in this case, this is a 6-node Kubernetes cluster with 1 master and 5 workers. We mainly focus on the workers. So on the workers, there is a Zookeeper, Kafka, and Cassandra cluster running, and a consumer application. We can see on the figure that 90% of the energy is used by the CPU for every node, and 9% of it is the memory. The consumer service uses 65% of the total energy, and this is followed by the Cassandra cluster and then the Kafka. For the nodes, they mostly use the same amount of energy except for the 5th node. So this shows that SmartWatts allows to highlight the energy hotspots of distributed services. SmartWatts have different industrial use cases. For Orange and Nokia, they use it to evaluate the energy efficiency of the 5G infrastructure backend services. So SmartWatts is running on Kubernetes and OpenStack clusters. And for OVH Cloud, they use SmartWatts to evaluate the energy efficiency of their public cloud infrastructure in order to provide energy efficiency metrics to their users. And SmartWatts is running on OpenStack clusters. To conclude, SmartWatts provide per container CPU and memory per estimation. It uses self-adaptive power models, so it don't require an offline calibration phase. It is lightweight and no external hardware is required. It's open source and freely available on GitHub. Thank you very much for your attention.